Lignin is an important value chain for going for a sustainable society. It can be used to replace fossil-based products.
Lignocity is a unique testbed in the world. We can produce lignin from different black licorice that comes from different paper mills, and we can scale it up from only a few grams up to tons. Lignin in one sentence is the glue in wood, but you can extract it in the process we do here in Lignocity. And instead of burning it in the paper mill, we can create a higher value with evaluating the lignin into different products. It can be in asphalt, it can be made carbon fiber out of it, and it can be made bioplastic and many other applications. The testbed is located as a neighbor to Nordic paper, where the black liquor comes from that we produce lignin out of.
Within the testbed Lignocity, you also get contact with the research institute RISE. We can help companies that are interested in the lignin value chains, from the raw material lignin to the end products.
So here at RISE we have resources to work on the lignin that produce in Lignocity. We work on the different applications such as thermoplastics, thermosets, chemicals and fuels from lignin. So in this lab we make lignin-based carbon fiber and use it in different applications. For example, in this car you can see the roof is a lignin-based carbon fiber composite that the carbon fiber were made here in this lab. Also this car has a lithium-ion battery that in this battery also we use lignin-based carbon fibers.
In Lignocity we want to welcome small and medium-sized enterprises that we can help to take the leap from idea to market in small and safe steps, which reduces the risk to scale up.
Our time here at RISE was a key in our development. It helped us to have our product ready for the market, and now we are moving on and starting our demo plant unit outside Stockholm, where we will produce 2,000 tons per year of our material René. This is one of the end applications of what we do at René, using lignin to make plastic bags. The name of it is René, and we can mix it with bioplastics or fossil-based plastics, depending on the applications you want to do with it.
Region Värmland is strong in bioeconomy, partly because we have a lot of forests here and skills in how to create different applications out of the wood, but we want to grow even better and bigger on the bioeconomy, and lignin is one track. Here we have space for new possibilities with conference room, facilities and laboratory. Hi everyone, and very welcome to Lignocity's first webinar of 2022. We are in a great company today, and especially a warm welcome to David Saitton Blomberg from RISE and René from BASF that will give us their presentations very shortly. If you want to see the film again, you can find it on the Lignocity webpage, and there you also have all the contact details if you want to find out more about Lignocity and RISE. So welcome to contact us. To have the best experience of this webinar, use the view setting, speaker's view. You find the settings in your upper right corner of the screen. So speaker view is the one that will show you the presentation enlarged and the speaker next to it later when we start. And you can communicate with us during the webinar by using the chat, and you find at the bottom of your screen. Just press that and then you can type a message to us. If you have any questions to the speakers, please type them there as well, and after each speaker we will respond to as many of them as possible. We are running projects within Lignocity, and this event is presented by the project Lignin Innovation. It is a collaborative project between RISE, the Kristinehamn municipality and Paper Province, and it goes for 2 years. It is financed by the EU structural funds, Värmland region, and by the project partners. And we also plan to do more events like this. So if you have input on who would you like to listen to in a next occasion, let us know, and we see what we can do to realize your visions. And this event is being recorded, and you will find this and the previous webinars also on the webpage LignoCity. Now, David, I want to see if you are on screen as well. It's always exciting to have so many people in company, but you don't see anyone. But David, I hope you are here.
Yes, absolutely.
Great. Hi. How are you?
Yeah, I'm actually I'm overwhelmed with all the participants actually. So I will try to do my best here.
I'm sure you will. So please start to share your presentation. And while that, we assume that you will also present yourself. Who are you?
Yeah, I can start with that. But I tried to share the screen, and
yeah,
if you see anything in the correct way, please shout.
Yes, we're getting there. We need the presentation mode, and we have got it. So it looks perfect. Please start, David.
Yeah, good afternoon, everybody. As you see here, my name is David Blomberg Saitton, and I work at the Department Biorefinery and Energy as a research and business developer. So I got the question from Maria if I could have a presentation on like chemical production from lignin, and I said yes, of course. So I will try to cover up parts of what we are dealing with on rice, actually mostly. I would say that would be covered, and also I have some my own reflections in the beginning here, so bear with me. I will come to some reactors in the end at least, but we start with that. So these are my own thoughts really to start with, because we have a new situation within the transportation sector. We need biofuels, we need different kind of chemicals to support that. We have a new situation on the electricity side. We have, well, sustainable water management is needed. Of course, in Sweden, where I sit, we have a lot of water, but there are places with a scarce amount of water. And all of these new factors that plays a role to the industry. And the last photo is actually the industry then. Probably we need an industry in transition, because we must start to use different types of feedstocks, and then you get different type of process streams probably, and then you need a transition in the industrial sector as well. So one of these materials, of course, is the topic of the day, and that's lignin. And lignin, how can that be used? Of course, you can look upon different chemical methods to make lignin into something that is useful for certain applications. So you have depolymerization, for example, so you can make smaller fragments out of lignin. You have liquefaction techniques, so it's pumpable. You can insert a huge amount of chemical modifications where you use different like electrophiles. You use different kind of chemical methods to make the lignin to have different properties. A lot of the lignin modification can need stabilization. You need some kind of fractionation, purification, isolation of the correct part of the lignin that has been modified or altered in some way to actually respond to the application that you want to insert it into. So that is on the chemistry side. And then, of course, you have sourcing of lignin. That's really important questions. are chemical mixtures accepted, or do you actually want to have the possibility to produce one single molecule, or can mixture be accepted in certain applications? Is it polymeric, oligomeric, monomeric components you're looking for, or can you have a mix also there? I was into this already, but are we supposed to produce drop-in chemicals, the exact same compound, so you can actually just drop in the green chemical into the existing process stream? Or do we need to develop completely new processes based on this, the feed properties of lignin? That is something that I tend to think about sometimes, at least. So we skip that. So the lignin field, research field is quite old. So you have, I actually looked it up yesterday. I found at least one patent from Germany from 1928, where they patented a process to produce vanillin from lignin. So it's really an old research field. And of course you have a lot of different, you can see to the left, a lot of different applications where you find lignin, or can find lignin. And as Maria also mentioned, asphalt, or it's carbon fiber, or it's hydrophobization of fibers, polyurethanes, carbon black, activated carbons, coatings, vanillin, and well, emulsifier chelating agents and concrete additives. And that is has been going on for a long period of time. And some of these areas, there are also already value chains present in the world where you produce lignin and they are used in certain applications. And some of these fields may be less mature products. So I start off with the sourcing of lignin, and I chose to present kraft lignin, lignosulfonates, and hydrolysis lignin. And kraft lignin, you have a couple of plants in the world, one in Domtar and one in Finland at Stora Enso. And of course, in Bäckhammar, this Lignodemo for, well, large amount of lignins, but still smaller than the full-scale implementations. So that's kraft lignin, and then you have lignosulfonates that they isolate at Borregaard in Norway, and also Aditya Birla Domsjö here, where I sit and look at the mill right now. They have a spray drying technique to isolate the lignosulfonates. And also one process stream that is starting to get more and more interesting is the hydrolysis lignin. And on the photo to the right, you can see a picture of the sunliquid plant that was Clariant just recently built in Romania. And there you have a third quite different lignin coming out from that process. So you have kraft lignin, lignosulfonates, and hydrolysis lignins. And of course, there can be other types of lignin as well. So I will start off with the liquefaction of biomass, it says here, but of course it's lignin. Maybe a copy paste error from my side, sorry. Liquefaction of biomass. So first of all, I like to talk about pyrolysis, and why the liquefaction also you can mention. Of course, liquefaction of a biomass gives new opportunities, altered structures, and a new type of biomass as compared to the crude biomass used in the process. So pyrolysis at Rice, we have pyrolysis in different scales up to 30 kilo per hour. And this barrel here is produced pyrolysis oil for a project called Biomates, as you can see on the picture. And for this process, of course, different types of lignin the function or the results from pyrolyzing lignin gives different types of product output. So you have a liquid, you have a solid, and you have gases, more or less like that, non-condensable gases. I also want to highlight here that you can use, of course, other types of material like plastic, mixed plastics, composites, and so. But pyrolysis oil can then be used as a precursor for chemical production. One type of pyrolysis that is present also at RISE is this hydropyrolysis. So actually, I will try to do like this, I think. So here we have the material feeder, and this setup is actually then in Piteå, RISE in Piteå. You have the material feeder, you have a drop tube furnace here where you heat everything, and you add then hydrogen at about 1 atmosphere's pressure into the whole system. So the pyrolysis oil, the material is pyrolyzed, you remove some solid residues, and the process gases goes into a catalytic reactor that you find here and gets affected, or you have a reaction in this catalytic region. And then you have condensing the products, and you have different types of the analysis in the end. And what you can, I don't know if you see this one, I can move it here. So what you can see, the output from hydropyrolysis is quite different than just thermal pyrolysis. You have a even more complex mixture. And depending on what type of catalyst you have, this is a platinum-based catalyst, or this is a zeolite catalyst. And there you can also see that you have different output from this hydropyrolysis rig. So this is one way to liquefy and upgrade, modify the lignin content then towards, in this case, monoaromatic hydrocarbons and phenols. So another technique that we have present also at RISE is hydrothermal liquefaction. And hydrothermal liquefaction compared to pyrolysis, is usually you have dry biomass. HTL, it's a water-based technique, also really old technique, very flexible on the raw material side. This process depolymerize the biomass, the lignin, and it also removes some of the oxygen, so you get less oxygen in the product. And of course, as in the previous case for pyrolysis, you have the possibility to use this raw material for chemical production. What we also found that was really intriguing was rapid heating and rapid cooling. Actually, then a continuous process would favor oil yields. So we did that at RISE. So we started off with this batch reactor, and we got, well, kind of a lot of char formations. So then we built up a semi-continuous process where we fed the biomass from this reactor into this preheated reactor here. And then when the residence or the reaction time was ended, we opened the next valve and we flushed it out to this cylinder here where we have cooling. So here in this process here, we have rapid heating and rapid cooling as compared to the batch system. And that actually suppressed the side product formation quite well. So we built up a fully continuous process based on these results. where we can have about 2 liters per hour, and usually we are around 10 to 15% dry matter content. And this pilot works at near supercritical conditions. So just some figures about the reaction conditions, quite high pressures, quite high temperatures, well, quite low residence time. And also you can use different type of catalysts then to suppress the side reactions. In general, you can say that the oil, the properties of the oil is something like this, and you can highlight, of course, the 2 in the bottom maybe. You increase the energy content quite a lot, and you, of course, then you decrease the oxygen content quite a lot. And the yield of this biocrude oil, the HCl oil, is somewhere between 20 and 70%, depending on feedstock and process. So how to produce chemicals from this HCl oil? So I will give this example. This is a liquid extraction sequence where you start with HCl solvent, HCl oil in an organic solvent. You add sodium hydroxide in this case, so you have high pH in the water phase. You do an extraction, and you get out something, an aqueous phase containing, then in this case we were aiming for phenolics. And then we have a really unpolar organic solvent washing out the really lipophilic components, and then acidifying, extracting back the phenolics. So we got an organic layer enriched in phenolics in this case. So what you can say about this is the solvent choice. The choice of solvent is, of course, really important to steer this kind of extraction sequences. And also, of course, this was a pH solubility extraction sequence. And what we got out, depending on how we change the conditions in this sequence, you can have fraction 4, that's the remaining HCl oil after the first extraction. It can vary between 22 and 69% on weight percent. And also enriched phenolics, you can vary between 27 and 67% in the trials that we have done on this HCl oil. So this is then, well, a technique to enrich or to isolate or so chemicals from an HCl oil. So I will touch upon some chemical conversions in the end, and I will start off with slurry hydrocracking and fluidized catalytic cracking. These are 2 techniques that actually are used and exist in full-scale oil refineries. But of course, we want to go bio-based on this. So bio-based oils from lignin can be used then, and the slurry hydrocracker is also equipped with a fixed bed reactor at the end to actually have further upgrading of the outgoing stream. And on this picture here, you can see the FCC, fluidized cracking, catalytic cracking system. So starting off with the SOC, you have feeding tanks and hydrogen, compressed hydrogen to feed into the reactor together with the catalyst in slurry, and also, of course, the feed. It goes into a reactor at a certain temperature, and then to a purification system that is downstream the reactor. So this is a high temperature, high pressure reactor for and distill off a portion of this to the low pressure and low temperature reactor. And this is maybe someone from PTO is present at this meeting, and if there are questions, I'm happy to invite you also to answer the questions if okay. But in this publication that you see down to the left, they were used pyrolysis oil as a co-feed in vacuum gas oil, and actually they looked upon different conditions, different temperatures, different catalyst load, and different residence time. And what you can find if you go from lignin to a pyrolysis oil and further on to this upgrading, you can actually find 56% of the biogenic carbon in the process stream, because VGO is a fossil feed from oil refineries. And in this process, of course, you remove the oxygen quite a lot. Hydrodeoxygenation is 94%. And the light fraction from these trials represented about 20% of the total yield. And this can also be used, this is me speculating a bit here, but the hydrodeoxygenation actually renders the pyrolysis oil much more stable than in the start. So stabilization of pyrolysis oil or HDL oils or bio-based oils, that I think is one of the important factors to be able to handle it in further downstream processes like distillations or whatever. And also I want to highlight something in the end here. It's a steam cracking unit that also been built at RISE in Piteå. And the steam cracking is, of course, a full-scale technique that is used to produce olefins. Usually you have a feed of LPGs, liquefied petroleum gases, or light naphtha. So it's rather small molecules that you feed into this steam cracking unit. So with the aim to produce then olefins, usually, like ethylene, propylene, butadiene, and the components like that. So this is a fairly new setup that we have at RISE in Piteå, and I think this will be a really interesting part of the future work that we're going to do, where we really want to produce chemicals. And this will be then a drop-in chemicals to the existing refinery structure, where you use ethylene or propylene plastics for producing plastics. So this will be very interesting to see, can we produce a bio-based oil from lignin that can be used for steam cracking purpose to produce these really key components, key chemicals in the chemical industry, ethylene and propylene, using then renewable feedstock. And this will be a work for us that lies ahead, because to my knowledge, we are just testing this so far, and it looks promising, and we hope this will be something really for the future when talking about chemical production. So with this, and I'm happy to have discussions, questions later on. With this, I will thank you for your attention, and also have some commercial for the new pilot facility that is being built in Örnsköldsvik. So we will build up this pilot hall and install a lot of equipment towards chemical production, material production, and biorefinery process development within this pilot hall. So this will be up and running in 2023. So I hope I see some of you in Örnsköldsvik quite soon. So thank you.
Thank you, David. And meanwhile, we're happy to welcome people to Bäckhammar, where we already have a hall, but it's smaller. And of course, we are collaborating on this. You do have received questions.
Yeah, good. We take them now directly. Perfect.
Yeah, the ones we managed. Then we'll let René in as well. We have a question that came rather quick. When liquid is added to make it pumpable, I assume it's the biomass, that's it?
Yes.
Is it always water, or would it be feasible to add a bio oil instead as the liquid to achieve the possibility to pump it?
Yes, it could actually be that way. If you could prepare a slurry, let's say if you have a bio oil of some type, used cooking oil or whatever bio oil, of course you can prepare a slurry based on with biomass into that type of oil. Yes, and that is actually interesting, really interesting case in some of the setups I showed you today. That could actually be a very interesting way to see if we can do directions like that. Yes.
Thanks. What is the source of hydrogen and consumption per kilogram? What is the yield of the oils?
Yeah, I showed some very broad figures, and of course it depends a lot. The yield of the bio oils is, if I refer to hydrothermal liquefaction, it's between 20 and 70% on weight yields. In pyrolysis, I don't dare to answer really, but if someone from PTO is here, you can just say, because you're much more convenient with that. That was one question of 20 to 70%, and that differs quite a lot between how harsh conditions you use, what type of feedstock do you use, and so on. So I stop with that.
Yeah.
And the hydrogen consumption, that was the next.
Correct.
Yeah, the hydrogen consumption, it's a really good question. From where do we get all the hydrogen that's needed for upgrading? If you're talking about chemicals, of course, you can sometimes accept oxygen still in the products. But when you're looking up on transportation fuels transportation fuels, usually you want to remove all the oxygen, and then you have to add hydrogen to remove that oxygen. And one thing that is interesting with the hydrothermal liquefaction is that you actually reduce the oxygen content just by this thermal treatment. So you can remove from 40 to below 20% oxygen, and then of course you don't have to use as much hydrogen as if you start with the actual biomass. So there you can save some hydrogen, but in numbers it's I can't really say, but it's a huge question.
Thanks. There are more questions, but we will let René do his presentation and then see what more questions come into that. You can read the questions already in the chat, all of you, and we come back to as many as we can. But we will let René from BASF come in and do his presentation. Welcome, René. How are you?
I just say that you feel free to contact me with any questions later on as well. Thanks.
Yeah, definitely. You can type your email, David, in the chat as well to facilitate. Great. Thanks. Hi, René.
Hi. I hope you can hear me.
Perfectly well.
Wonderful. I'll start to share my screen.
Yes.
And let's see if we can start right away.
Yes. And where in the world are you right now? Are you in Gothenburg or?
I'm located in Gothenburg. Working for BASF here as a scout with a strong technical background. I mean, David, we have talked to each other. Looking for opportunities, looking for nice projects together with the chemical industry and let's say with the institutes, with small, medium enterprises. helping them to develop into, let's say, bringing BASF to the next level. But I will talk about that a little bit later. Let me just start with my presentation right away. I have separated this in 3 parts. First, a little bit as is usual for everybody, except many of you, I expect you know BASF, but to give a little overview about BASF. Then I would shortly go on the biosynthesis of lignin. How is it synthesized in nature? And then it's quite obvious that you can use this knowledge about how lignin is biosynthesized to see the difficulties in applications with lignin, where you start to get more and more, let's say, into the detail about the technical properties of lignin, which until today led only to very small applications. So this is something where maybe this talk can also inspire you to get up with new ideas and get some new, let's say, spirit for this. So let me start with BASF. Our purpose is we create chemistry for a sustainable future. That means for every decision we take, it has to at least improve our total sustainability impact. Some figures to give you a rough overview. We are company with a sales revenue, with a sales of roughly 60 billion euros in 2020. The figures for 2021 will be published in February by the board. But the most important thing is we do this around the world and with together roughly 110,000 people. Our strongest commitments and our strongest task for the future are reducing our carbon footprint, as we are a fossil company, by another 25% until 2030. And we are really aiming for a net zero emission until 2050. Just to give you an impression how this should look like, we started in 1990 to measure, and this is normalized to 100% on the left side. And we already managed to decrease our carbon footprint in production by roughly 50% until 2018. And now the next 12 years until 2030, we have to reduce another 25% of our total CO2 footprint. And this is, let's say, in line with the development since 1990. And it's obviously that we have to accelerate this until 2050 to become net zero then. So ladies and gentlemen, keep your fingers crossed. We are really on a hard way here to get carbon neutral. Some key elements of this is our energy consumption. And I just would like to highlight 1-2 projects here where we are now starting to heavily invest into wind farming and renewable energy production, which is one strong pillar on the way to become carbon neutral. But this should be this for the company presentation. Please remember, we are on our way to become carbon neutral by 2050, and we need to accelerate our current ambitions to be much faster and to reach this target. So I would like to give a little insight about the biosynthesis of lignin now. This is maybe known to you here in Sweden from a vast majority of the scientists as forest industries. So please don't correct me if I'm saying something wrong. I'm just a rough chemist in this respect. So from our perspective, the lignin is synthesized in the last moment of the wood cell generation. So first of all, you build up the cell structure with the cellulosic and the hemicellulosic material. And in the end, lignin monomers are entered into this framework, and they are polymerizing there in the framework to stabilize it and to fix it in that position. And this polymerization process is a radical process. So this gives the challenge to the cell to stabilize radicals and to make this possible. For the chemists under you, I cannot avoid it. I'm a chemist by training. I have to show at least some molecules here. And what you start here from nature is how can you polymerize materials within the cell wall? And it turns out that this is the main starting material. I hope you can see it. It's quite small. Is coumaryl alcohol derivatives. And this is down to the left side. And if you would like to see how can nature produce those coumaryl alcohol derivatives here on the left side, let me take the pointer. Exactly. So this coumaryl alcohol monomers, they look similar like a styrene monomer in the chemical industry. So this is one of those starting materials from nature, which is polymerized. And the easiest way for nature to produce it is starting from phenylalanine, one of the amino acids. So derivatization to get it there. And then this material is introduced into the cell wall and polymerized. Now what we see in the lignin molecule itself, we see much more substituted coumaryl alcohols, especially on the aromatic ring. You find a lot of methoxy groups, and they have a real very key function in stabilizing radicals. So what happens is you generate a radical at one of those molecules here, and will be stabilized at the phenol function. And then the next monomer is entering into the system. And this radical stabilization at the phenol function here is stabilized by methoxy functions next to it. And that's why it's getting so complicated to remove lignin from the cell wall again. How does it look in the end? Let me just show you one of these, let's say, artificial molecules drawn. This is not how lignin looks like. This is a kind of assembly how lignin could look like in some cells, but it's different from plant to plant, and it's also different from species to species. So what you see here is everything starts with one of those condensed tetrahydrophoranic rings, and this is mainly the starting point, and then syringyl alcohols, guaiacyl alcohols, they're all added onto this chain to a certain end. And the next monomer increase will be, it's on this end here, or on the other end over there, where you can stabilize the next radical and then it's attached. So this is a very, very stable function. It has a high resistance against oxygen, against other radicals, and it has also a high resistance against acid and base attacks. So this is a real stress-resistant molecule, I would say. So what is necessary to get this out of the cell wall again? And then we are right now in the typical paper and pulp and paper industry. What could you imagine? How can you get this out of your cell walls again to get the cellulosic material at hand? It's the key function is get this material into solution. And this is performed by removing the methyl groups at the aromatic rings. And this is usually done by sulfate processes or even very weak nucleophilic direct sulfur. Like mercaptan, I would say, in German. So this is the typical Kraft process or even the sulfate process. They have weak nucleophiles to remove the methyl groups and to deprotonate the phenols. And then lignin becomes soluble in water, and then you can track it out of the material. So this is the starting point for applications of lignin. So the next step is, how can you do, what is the properties you can do, how can you perform lignin, transform lignin into something really useful? And the key issues in lignin and in lignin handling is, where do you want to go to? And from the chemical industry perspective, we have several challenges we are putting on the table right now. Our typical products have a very clean, a very versatile technical property. And if you look at lignin, the first thing you realize, it smells. This comes from the production process where sulfur is involved. And this is like something, if you want to sell your material in the end, your customer is mostly looking for something which is not smelling. So it is quite obvious that the lignin you are extracting from wood needs, after post-treatment, to get it into a usable form. The second thing, as I mentioned before, is reactivity. The lignin you get out of the wood today is quite poor in reactivity. You have already, let's say, removed a lot of methoxy groups. It's phenolic groups, which are chemical-wise not the most attractive reactivities. And regarding a very big lignin molecule, which is still in hand, this is, let's say, poor from our point of view. And now talking from a very industrial chemical point of view, lignin has to be, let's say, put into solution, has to put into a liquid form that makes it much more easier for the chemical industry to use it. Normally, we don't have reactions with gases. We try to avoid reactions with solid compounds. Our task is mainly get things soluble, pumpable, and then we can process it. And this is, unfortunately, with lignin, you need quite a caustic condition to get lignin into aqueous solution. So therefore, solvents like protic polar solvents or aprotic polar solvents are, let's say, necessary to process lignin. On the other hand, those take a tremendous cost in charge. If you want to process lignin and you have to use a solvent, the costs for processing immediately explode. So, two alternatives come immediately into my mind. What can we do with lignin then if it's so poorly processable? The first thing is you can use the lignin you extract from a process like a craft process, as you see it in Beckhammer. You can take such a material itself. You release the lignin as a powder from your process, and this material is, let's say, has a certain surface activity. It is brown. It has a chemical functionality. So you should try to use this material direct in applications. For example, as a starting material for polymerization or as a filler in materials. The problem of this is lignin is very specific in its properties. So the value of the property is increased. And unfortunately, if your properties are quite defined, the application are limited where you can use it. So that's the one part, use lignin directly as a material. On the other side, it is interesting to use the lignin as a chemical starting material, as a chemical raw material. And that is a clear necessity in bringing the molecule down, degrade the molecule to small chemical entities. And that is something where the chemical industry has a strong demand in small molecules as new feedstocks. This requires that you degrade lignin, to break down lignin to a very small molecules, and that you need to purify or separate those molecules from each other. And this is a kind of way, then the chemical work really starts. This is, let's say, time consuming, energy consuming. But the reward you get is the volume you make accessible will be, let's say, very much appreciated from the industry. So you have a strong volume demand on renewable raw materials right now. And only by bringing molecules down to a certain size and then to a unique form, you could address those volume demands. So let me now form a little bit more into the no, I'm sorry there. Okay, go a little bit more into the lignin applications right now. What you see here is I would like to go a little bit more in lignin as applications as they exist right now. Today, there are many ideas about how to use lignin in applications, for example, in polymer applications. If you remain this as a macromolecule and leave it just untreated, you could use it directly as a filler in polymers. So bring this material into polymers and just replace, let's say, a fossil filler or a clay filler with lignin molecules. And this would immediately get your bio-based content of that material you're selling afterwards to a manifold. This is applicable in polyurethane foams and polyacrylate resins and so on. So just use it as a filler. Lignin has one of those advantages that it has a kind of a barrier function against oxygen. So this is something of the material properties you can use if you just put it in as a filler. The other topic is try to use it as a functionalized molecule. You see this in lignosulfonates, for example, where you take the lignin and you perform one single chemical step up front to activate the surface of lignin, for example, by using propylene oxide to modify the surface of lignin. And then it gets involved into chemical reactions afterwards. So it's not used as a filler, but as a direct active ingredient in your formulation. This is interesting for phenolic formaldehyde free adhesives, where you replace the phenol formaldehyde moiety with, for example, lignin moieties. And this is, let's say, one of those developments which is coming up in the future. Looking into others, like replacing other materials, it's always important that you have already an existing product where you try to meet the properties. And this is where you see the challenges and it's limiting in your applications. So that is part of one. The other part is if you break down lignin into monomers. I can clearly state from the chemical industry, we are very interested in raw materials like toluene, benzene, so aromatic structures, phenols. This is something where we are immediately saying this could be directly converted into new bio-based chemicals. And we have a demand for that from our customer side. What you see especially is if you look and if you remember the lignin monomer, the lignin molecule, I'm sorry, if you remember the lignin molecule, which is placed up here, you see that there is a mixture of aromatic compounds and normal aliphatic compounds in one molecule. So by generating a fragmentation of lignin, you would immediately get access to ketones and aldehydes and let's say C3, C2 figured molecules. This is something where I would say from a chemical point of view, this is interesting if you can get those materials as a pure form. Yeah. Now, but coming back to the statement from the lignin biosynthesis from before, lignin is unfortunately designed to withstand chemical stress. So it is quite resistant against radical treatment or against oxidative or high or reductive treatment. So this makes it a little bit difficult. How can we attack lignin and break it down? And yeah, you mentioned it, David. Lignin is long known, and there is no 100% solution developed today. So I think there's still room for improvement. I would like to come to the end of my presentation with 2 more slides. One is just to give you an overview how big our own demand could be. If you see this slide, I will not go through this in detail, but you have to read it from the bottom to the top. We are starting normally with crude oil, like naphtha is a fraction from crude oil, or we start with natural gas. And we perform 3-4 reactive steps and diversify with every step even more until we end up with monomers like toluene or like aniline or like butadiene, methanol. This is what we do. And we are looking for new raw materials. And these are the basic raw materials for our chemistry. Starting with lignin, breaking down lignin to monomers, we could immediately identify several entry points for interesting compounds on this level. So this would be very interesting, for example, to discuss with David on the liquefaction of lignin. What are the monomeric contributions in his mixture and where do they fit into this path? And just for the demand alone in Germany, simple Germany, we have a demand of roughly 2 million tons of naphtha, which is down there in the corner. We would need that material, if you would like to be 100% neutral, 100%, let's say, fossil free, we would like to replace those 2 million tons. So the demand is quite huge. Coming to the end, yes, we have a very interesting lignin as a carbon source for the chemical industry. The problem is the correlation about the monomeric lignin big structure or the small fragmented structures. The bigger the lignin molecule is in the application, the more limited the applications are. And if you break it down to small molecules, it gets really interesting. The value is reduced, but the volume is immediately rising. Yes, I mentioned lignin is designed to withstand aggressive chemical conditions. So the last word is not spoken on this, and we need to solve it not today, but long term. This will be a very, very interesting task. And with this, I would like to end my presentation. And thank you for listening. Thank you for the attention, and I'm looking forward for your questions.
Thank you very much, René. We learn a lot today, especially me not being a chemist, but very interesting. And the first question that came in is, what proportion of your production volume will be bio-based by, say, 2030?
Well, that's a difficult question. I think there's no statement for bio-based right now. Our share is more driven by our customers' demand. So I would expect we need, well, guessing, we'd expect at least 100,000 tons of renewable raw material additional to what we already set in. So we are talking about really tremendous numbers. The problem is more, how can we fill this? How can we fill our front end with material? The raw material availability is stressy, let's put it that way.
Right, and here is a question that your flow chart showed entry points for lignin after degradation. But what about lignin as a modified reactive polymer? What do you think about polymer industry entry points for lignin?
What can I say? This is important. We have to overcome some challenges here. I mentioned the smell of lignin. I mentioned the transparency. I did not mention the transparency. Lignin is brown today. It's absorbing light. And you know yourself, you would like to have a plastic or if let's say a non-bio-based product are normally clear, transparent, or white. And if we are looking for applications for lignin here and looking as a compound somewhere, we should also tackle the challenge in color, in transparency, and in smell, of course. I would like to have something, but then we need a method to make this, to overcome this.
So challenges to overcome.
Of course, I mean, it's not easy.
Yeah. Do you see any potential for lignin nanoparticles?
Well, it depends on the properties. Nanoparticles, is this kind of soluble? Are they non-soluble? Are they dispersible? What it depends on the properties. I see a lot of potential. Then I would start to question myself, what is the performance benefit of a lignin nanoparticle against graphene or against another dust particle from another source? And if you can, let's say, by surface functionalities on lignin nanoparticles solve another problem which is already existing, which is not solvable by other nanoparticles, there immediately we have a clear entry point into market.
Very good, thank you. And I'm not only the presenter of this, I'm also the time police, and we will need to end this. There are some questions left, but I promise that everyone that has been entering their email addresses properly by registering for this event, we will come back to you. So I will ask you, David and René, that when I ask you to type the answers, I will then forward them to everyone who's been listening today, so that we get a complete response. Really great interest, so many listeners. Thank you so much, David and René, for sharing your thoughts and knowledge about this, and more is to come. Next webinar we will present the 24th of February, and the content is not yet fixed, so watch out in your email box or on social media, and I'm sure you will not miss it. So thank you very much for participating, both everyone listening and David and René for talking.